Our next speaker today is Ben Webster from University of Waterloo and the Perimeter Institute, and he's going to tell us about tensor products and categorification.
All right, thanks so much to everybody for showing up and for the opportunity to speak. So what I wanted to talk about today is sort of one approach to understanding the representation theory of Lie algebras, also Lie superalgebras and quantum groups, and somehow I think the stuff I'm going to say is maybe a little more interesting in those slightly more exotic cases, but I'll at least start by talking about Lie algebras so things are a little more familiar. Now, somehow what I've gotten interested in representation theory is really understanding categories of things. What's the structure of some category, which maybe doesn't sound that interesting if you're thinking about finite dimensionals for semi-simple Lie algebra, because of course it's a semi-simple category. There's interesting stuff going on if you think about it as a tensor category, what happens when you tensor things together, but just as kind of a bare category sitting on its own, it seems rather boring. But incorporating this tensor structure, in particular, incorporating the functors of tensoring with other more interesting categories of representations is actually a very powerful tool. And if there's sort of any takeaway you should take from this talk, it's that that's a really powerful approach and you can get some interesting things out of it. So in what sense can we kind of understand tensoring with finite dimensional modules? This seems kind of a hopeless task because there's so many finite dimensional modules. How can you understand tensoring with all of them? The answer is it's actually easier than you might think. There's sort of less going on in that category than you might imagine just looking at all of the finite dimensionals. And the way to break this down is to first look at the action of the center of the universal enveloping algebra. And I don't just mean on the finite dimensionals, I mean on the guys you're going to tensor them with. So I'm going to basically throughout be looking at modules which are locally finite under the center. So if I take a vector in that module and I act on it by the center of the universal enveloping algebra or the quantum group, I get a finite dimensional space. And this is nice because that means I can apply Jordan decomposition to elements of the center. And in particular, if I have a module like that and it's indecomposable, well, Jordan decomposition actually tells me that every element of the center has to be acting by a scalar plus something nilpotent. So you're sort of maybe used to the idea that it should act by a scalar. That's on irreducible things. On an indecomposable thing, it might act by scalar plus something nilpotent. And so it's some power of a maximal ideal in the center acts trivially, and we can break up our modules according to what's their generalized central character, what that maximal ideal is. And I'll just note for usual Lie algebras, so I'm always going to use lowercase Fraktur letters for Lie algebras with no super and capital Fraktur for superalgebras. There's a nice description of this max spec of the center. It's the dual of the Cartan mod the action of the Weil group, which is very close to being you think about a module with that highest weight or that lowest weight, but you have to decide which one it is, and you get a different answer for the two of them. So you have to incorporate this row shift to deal with highest and lowest weights. All right. So as I was saying, I want to kind of look at my category of modules and break them down according to how the center acts. So given a maximal ideal in the center, I can look at the category of modules which are killed by some power of this maximal ideal. So the scalar given by that maximal ideal tells you the scalar that the center acts by plus something nilpotent. And on an object of this category, I have an action of not just the center, but on every individual object, I get the center mod some power of the ideal. I don't know what power of the ideal it is. So to put them all together, I have to take the inverse limit and take the completion. All right. And now, having gotten this set up, now I can look at how finite dimensional modules act by tensor. So I can take something with a fixed central character, generalized central character. I can tensor with a finite dimensional, and then I can project to, well, maybe the same central character or maybe a different one. And the functors that come up after you say, well, that might not be indecomposable. Let me take the summons. Oh, well, I might want to add those together. Let me take sums of those summons. Those are called projective functors. And they really are the projective objects in some category. So that's kind of where the name comes from. And this category projective functors controls tensoring with finite dimensionals, but it's not nearly as big as the category of finite dimensionals. So I'm going to specialize for now to looking at the principal block, the one containing the trivial module. And in that case, the category projective functors going from the principal block to itself has as many indecomposable objects as the Weil group. So there are infinitely many finite dimensional modules, but all of the structure and how they act on this piece of the category is captured by Weil group many things. And that category actually has a nice description. It's the Zergel bimodules over this completion of the center up to some completion. Yeah, so they're a completed version of Zergel bimodules using this Harish-Chandra homomorphism. Okay, so this is a very combinatorial category. There's lots of interesting stuff about it, and it's really controlling this action of tensor product. So what can we do here? Well, by comparing with Zergel bimodules, we see that we actually get a categorification of the Hecke algebra of our group, whatever that type is. It's key to this approach of Zergel to understanding category O, and in particular showing that category O is causal self-dual and has a nice graded lift. Essentially, right, we can look at these completed Zergel bimodules and say, oh, well, if I got rid of completion, I would have a category of graded bimodules over this graded polynomial ring. So everything inherits a graded lift. And in particular, this is sort of at the heart of Elias and Williamson's proof of the Kazhdan-Lusztig conjecture. By turning this question of what is the structure of modules over this group into something purely combinatorial, then they can do a combinatorial calculation to show that the multiplicities of simples and vermas are given by Kazhdan-Lusztig polynomials. But there are some real flaws here as well. So one is, this is only about regular blocks, doesn't cover singular blocks, doesn't cover other cases like parabolic category O. Those defects aren't so bad. They can be kind of fixed in this framework, but it does make things more complicated. And it just doesn't generalize to especially the super case, right? You're just getting some more complicated category of projective functors if you went to the super case and looked at tensor product with finite dimensionals. All right, are there any questions? So this is kind of the, you always have to be careful about using the word classical when you've been introducing quantum groups, but kind of the older version of this, sort of pre-1990s.
Would you be able to explain why it doesn't generalize to the super case easily? What's the obstacle?
That's a good question. What is the obstacle? I mean, the most obvious obstacle is you're using the fact that in a block of category O, there are Weil group many objects. And that's just not true in the super case, right? Like if you have an atypical block, you're going to have infinitely many simple objects. So you sort of expect like, somehow the way this works, this thing about W many indecomposable objects, that goes back to Bernstein and Gelfand. And it sort of uses the fact that you can control a projective functor completely by how it acts on a dominant Verma module. And well, in the usual case, in the usual Lie algebra case, there are only Weil group many different Vermas that can come up when you hit that with a projective functor, and in the super case, there are infinitely many.
So actually, can I ask a question? I don't want to take more time, but what about the action on, say, the trivial block in the Harish-Chandra category for some symmetric subgroup?
That's an interesting question. That's something I haven't thought very much about. It's just sort of something I could have sort of put that into this talk as like, oh, this is another thing that would be interesting to think about that I haven't given much consideration to.
No, but that's an ordinary situation where you don't have while group many objects. I mean, so if you add that might be helpful also for when you try to superize or quantize. Okay, sorry.
Yeah. Well, you know, somehow, yeah, it depends on your perspective, but somehow if you do the super stuff in kind of easy cases like GLMN, I think that might actually be kind of easier than, you know, trying to do other weird symmetric ones. But maybe I'm wrong. I don't know. All right. So in order to understand these more general cases in some nice systematic way, we have to sacrifice working in all types at once. And maybe now you'll see why GLMN scares me less than whatever random symmetric pair you might bring up, which is in GLN or GLMN, we have a distinguished pair of dual modules that are particularly nice to look at. So the defining representation, which, you know, in the usual Lie algebra case would just be Cn. For GLMN, it's CMN, and it's dual. And so you can look at tensoring with that guy and its dual, and you'll get some interesting functors on your category. And I like to show things graphically, so I'm going to represent tensoring with the standard module as an up arrow and tensoring with its dual as a down arrow. And there are some natural functors between these, and they're kind of all built out of a few relatively simple ones, which are, there's a dot, which represents the action of this Casimir type tensor. There's the swap, where you switch to tensor factors, and then there are junctions that come from the fact that these representations are dual. All right, and you can actually describe all the relations between these natural transformations, or at least enough relations. I mean, somehow I don't necessarily want to make a precise claim about these being all the relations, but somehow these are the ones you need to make things work. I'm not going to get into these just because we don't have very much time, so I'm happy to talk about them later, but this is what Brendan and collaborators call the affine-oriented Brouwer category, or the level 0 Heisenberg category. And I should note, there's, due to work of Brendan Savage and myself, a Q-deformed version of this category, which gives you the action on UQ of GLMN. All right, so that's good. That's sort of, you know, some fun diagrams to play with. But how do we see the projective functors and this block decomposition? Well, we can actually see the center of GLM, the U of GLM in this picture. It's given by bubbles. So these are natural transformations from the identity functor to itself. So they're elements of the center of the universal enveloping algebra. And we can actually separate the blocks by looking at the eigenvalues of these bubbles. And there's some very nice combinatorics behind this, but I just don't have time for it. But in particular, a natural way to break up these functors is to use the diagonalization of this natural transformation I called omega. Remember, that's the dot. And again, it might not act semi-simply, so I'm taking generalized eigenspaces. I'm diagonalizing the semi-simple part. So if you sort of follow through all the combinatorics with this, each one of these summons sends one block to another particular block that depends on I. So this is kind of getting you this decomposition of tensoring with your finite dimensional representation in all the different blocks that it can land in. Was that a question or just a stretch? Okay, I guess it was a stretch. All right, but I like the combinatorics of this much better for reasons I'll explain in a moment. And the reason is that these functors EI and FI satisfy the Chevalley relations of SL infinity. So this is, here I think of having the integers, 0, 1, -1, etc. And I think of those as an infinite length Dinkin diagram. And these EI and FI, they satisfy the relations. If you look at them on the Grothendieck group, they give a representation of GL infinity, but they're really giving you something much stronger. There's this notion of a categorical action of a Lie algebra, which was originally defined by Ruquier and somewhat independently by Havonov and Lauda. And in fact, these functors give you an example of one of these. So this is sort of my replacement for Zergel bimodules. It's a categorical action of SL infinity. And that works, incorporates all the singular blocks, and it works for superalgebras SLM. Now, I'm not going to try to write down the definition of a categorical action. I think it's just a little too long. I'm already halfway through my talk. So let me just say it's defined by, I have functors E and F, and I have natural transformations between them that satisfy some relations, and those relations force those functors to satisfy the Chevalley relations. And this is a very powerful idea because the different categories of modules over GLN or GLMN can be understood by what representation of SL infinity do you get from their Grothendieck group. So for example, the finite dimensionals, well, you see this enormous difference between the finite dimensionals over GLN and GLMN. So for GLN, they categorify this wedge product, which is a minuscule representation. And that's very nice. It gives you this sort of very simple structure of finite dimensionals. We know it's a semi-simple category. But over GLMN, I get a tensor product of two wedge powers. So with the two different kinds of vector space, the even part and the odd part, give me two different tensor factors, both of which have wedges on them, right? The way to think about this is to get a finite dimensional of GLMN, you should take a finite dimensional of GLM and a finite dimensional of GLN and induce them up to get the Katz module. So because this is a much more complicated representation, for example, it has infinite dimensional weight spaces, that's telling you you're getting a much more complicated category. If I want to understand category O instead, well, all I do is I replace my wedges with tensor products. And another sort of nice guy to consider is what's called the category of Whittaker modules. And that gets you symmetric powers of C infinity. And again, over GLMN, it should get you symmetric powers of these two guys. I should say this last one is sort of isn't really written down properly anywhere. But if you read this paper of Brundon and Goodwin on Whittaker co-invariants for GLMN, it's essentially in there. They just sort of never actually say the words. And of course, I only have so much room in the slide, but there are many other versions of these categories. For example, you can take parabolic category O, which will give you sort of a bigger tensor product of wedges, but not going all the way out to a full tensor product. There are also non-principal Whittakers that will get you tensor products of symmetric things. I don't really have time for it, but there's also this category of Gelfand-Cetlin modules, which has kind of gets you another interesting representation that doesn't match any of these guys. All right, are there any questions?
This notion of categorical action, it's just, I guess maybe the main point is that it's invariant under equivalence of categories.
I would say the main point of it is if you have a vector space and you know that you have a SLN action on it, well, suddenly you have a lot fewer options for what your vector space could be, right? Because you can understand what the whole vector space is by understanding what its highest weight vectors are, for example, right? And this notion of a categorical action plays a very similar role. So in particular, there's an essentially unique way to categorify simple modules.
Okay.
And I would just going to state this on the next page. in essentially all of the cases on the previous slide, that category is uniquely characterized by having a categorical SL infinity action and a few additional technical properties. So there's this notion of a tensor product categorification, which I developed with Losev, which is a bit more than just having the Groton D group be the tensor product. Somehow the tensor structure is really kind of somehow built into these categories. In all of these cases, it's basically that you have some sort of standard modules. So in category O, you have Verma modules for finite dimensionals over SLMN. You have these CATS modules, and there are similarly kind of standard versions of Whittaker modules. And that you have sort of reasonable behavior of taking those, tensoring them with the finite dimensionals you're interested in, and you get a nice filtration by modules of the same type. That's kind of the key extra property you need to incorporate. So in particular, this uniqueness actually allows you to prove that in all of these cases, characters of simples can be computed from the canonical basis of the corresponding representation. So in particular, this proves that category O over GLMN and these related categories have a graded lift and are causal. This is a nice kind of homological property that we've known for a long time for category O over usual Lie algebras. It gives a superduality-free proof of this Brundin-Kazhdan-Lustig conjecture that tells you the multiplicities of simples and Vermas, or you could say the characters of simples over SLMN. This had been proven earlier by Chen and Wang, and then there was later work of Chris Leonard that kind of unified these two proofs, but those used superduality, which is sort of, I don't know, it's a very powerful idea, but it's also a very confusing idea. So I kind of like not having to use it. And it shows that this sort of SL infinity action replaces Zergel-Bi modules. And I'll note one kind of interesting thing this gives you is if you go to quantum groups with a generic Q, you get categorifications of the same thing. And so you can actually use these uniqueness theorems to show that the category doesn't change when you go from the classical object to the quantum one with a generic Q. It's kind of an interesting thing that involves using this quantum Heisenberg categorification that I mentioned earlier. Okay. And if Q is a pth root of unity, then this changes to not an SL infinity action because I don't have distinct eigenvalues for all the different elements of Z, but I just have my powers of Q. So I get an SLP hat action. So I have 1 Q, Q squared, Q inverse. And these give me a copy of the SLP hat Dinkin diagram. Similarly, if I go into some representation theory category and characteristic P. You can consider all the categories we just discussed in this situation. The uniqueness argument breaks down. So there's sort of some interesting mystery here about what you need to do. But now the case of finite dimensionals is interesting. There's a theorem which I'll sort of ascribe to Risch and Williamson. Again, I'm kind of slightly changing what they said, but essentially what they were showing is that the category of finite dimensionals, they were interested in the algebraic group GLNFP, but the quantum group GLN, with Q a pth root of unity is sort of a very similar object. They're the unique categorification of this wedge power in this characteristic. So there's sort of, when you construct the categorification, you get to put in the characteristic of your base field, and you either get this root of unity or FP picture, depending on what you put in. And in particular, the principal block of finite dimensional modules in either one of these cases is the unique categorification of the anti-spherical module over the affine-Hecke category. And for them, that was kind of the point. They were interested in general, for all types, proving that you would get the sort of unique categorification of the antispherical module in the affine Hecke category out of the principal block of representations of the corresponding algebraic group. But somehow thinking about this SL infinity picture made it easier to prove that. All right, I'm quite short on time. I should stop at, wait, should I be stopping right now? Organizers?
You have 4 minutes. You have 4 or 5 minutes, actually.
Okay. All right. Well, let me just really quickly say, I mean, somehow this last section was meant to be very speculative, so that's fine. What can we do to generalize this to other types? Well, if you're interested in types B, C, and D, there's an obvious thing you can do, which is replace the Heisenberg category with the Brouwer category. So that was called oriented Brouwer before in Brundon's terminology. Now we're just going to take normal old Brouwer. So we can tensor with the vector representation, and now we don't have to worry about a representation in its dual, because there's only one, it's self-dual. There's a similar description of a category, which is essentially the relations of Nazarov-Wenzel algebras. And Ruizong proved that, in fact, this sort of combinatorial category acts on modules over in these types, which you can sort of unify by looking at the superalgebra OSP M2N. And just as before, we can decompose with respect to the action of the Casimir. I sort of skipped the combinatorics of exactly which Casimir you want. Now you have to actually be very careful about it, but it's okay. You can make it work. And well, what do you get? So, you know, somehow the point of this last section of the talk, which I should be wrapping up very quickly, is, well, it's a little complicated what you get. So if you look at z plus tau for 2 tau not an integer, so integer and tau not an integer or a half integer, then you just get this categorical SL infinity action back. And so it looks exactly like the representation theory of type A. This is something you could sort of, I think, deduce from earlier results in representation theory, but it's a nice kind of unifying picture. Now, this doesn't sound that interesting because these functors act trivially on integral blocks, but they will act after you deform an integral block. So if you look at deformed category O at the generic point, for example, you'll get this SL infinity action. On the other hand, you get something a bit more interesting if you look at functors where I is a half integer. So 1/2 plus z, you get a categorical action of the quantum co-ideal subalgebra for this Satake diagram. So you look at the half integers, you look at the involution that comes from negating. And I'll just note this kind of matches up with work of Bao and Wang, who proved this Brundon-Kazhdan-Lustig conjecture for OSP. And they didn't use the fact that you have a sort of strong action. So again, implicit in this theorem is that there's actually definition of a categorical action of this quantum co-ideal subalgebra. But they heavily used that the Grothendieck group of this category O can be identified with a particular module over this quantum co-ideal subalgebra. And well, if we take integers instead, we would expect to get a categorical action of a similar quantum co-ideal subalgebra where you take the integers and take the involution given by negating, but we don't know what that is. So we don't have a good definition. There should be a hint in these I divided powers, which Stefan mentioned in his talk. And one can conjecture that once one has done that definition, then all of the categories we discussed before will be characterized and given a graded lift by their categorical module structure. And I think I'm officially out of time, but let me just say, if you go to this characteristic P case or P through root of unity case, you should also expect the finite dimensionals. Oh, I put the wrong thing here. That should be wedge n of this guy. I don't actually want that star. That these finite dimensionals will also be uniquely characterized as a module over this quantum co-ideal subalgebra. And that this should, again, prove this theorem, which Rishin, Williamson, and Achar and Makasumi have proved in a different way about what the principal block of this finite dimensional category is. All right, I'll quit there. Sorry for going a little over time.
Yeah, thanks, Ben. So are there any questions or comments for Ben?
I think we should first unmute and just thank the speaker before going to questions.
Okay. Stefan? We cannot hear you.
I was just clapping, sorry. I didn't mean to ask a question at this point.
Oh, somebody wants to ask a question, so just go ahead.
I have a question.
Mm-hmm.
I just want to ask whether you could say something about how the SL infinity action allows you to prove causality.
So the important idea here is, so I mean, the short answer is you prove a uniqueness theorem, and then you find a different version of a category that also satisfies the same uniqueness theorem, which is causal. So somehow the idea behind this is basically that this uniqueness theorem shows you that you can identify it with this tensor product, and any question, causality is a question about X between two objects, and you can answer that question about X by taking these infinities and replacing them with some finite K. And then, well, you've got a tensor product of modules over this finite K. And we know another categorification of that in terms of parabolic category O. And so we can use the causality of parabolic category O in type A to kind of transfer this over to GLMN. So I mean, on some level, it's very close to this superduality picture. So this work of Leonard I mentioned, I think actually sort of proves using superduality that the same result is true.
So I have a question. So the uniqueness theorem that you mentioned, is it some statement like the category of representations of, let's say, SL, some category of representations of, let's say, SL infinity is equivalent to some category of categories with SL infinity action?
So I mean, what this uniqueness theorem looks like is you sort of say, okay, given a tensor product of simple modules over, let's say, so, I should say I kind of was being a little sneaky here. There's sort of a nicer statement for representations of finite dimensional Lie algebras, and then you kind of sneak this SL infinity picture into it by saying, oh, well, any question about this SL infinity I can kind of reduce to something in finite type. So in finite type, the statement is, you give me an ordered list of irreducible SLN or any other type representations, and there's a sort of unique category whose Grothendieck group is the tensor product of those guys, and which has a number of other structures. So, the most important ones are that it has this categorical action on it, and then it has a sort of version of standard modules, such that when you take a standard module and you act on it by one of the E's or the F's, you get something that's standard filtered in the correct way. And this is always pretty easy to check in these representation theoretic categories.
No, I was just wondering if you could organize the categories with those properties into two categories, and then maybe.
Yeah, this is actually a very tricky point, because so the thing that's extremely annoying about this, right, is I say, okay, you give me, it really is like a list of highest weights, and I tell you a categorification of the tensor product, and there should be some internal consistency there, where if you jam two lists together, you've kind of taken the two categories and tensored them together.
Yes.
And at the moment, it's still a bit unclear whether that's really true.
Okay, but that's what, there is some structure, there's some monoidal structure in this two category, which is.
Yes, well, we'd like to define one, and Ruquier has kind of claimed for years that he kind of knows how to come up with one, but the details are very difficult, and I've sort of never been able to check that what we're doing is this sort of claim thing that Ruquier is doing, and of course he never publishes any papers, so it's a little hard to confirm. So yeah, no, that's a very annoying mystery. So sort of what you get is if you jam two lists together, then the thing you get from the longer list has a kind of decomposition where it's associated graded is the kind of naive tensor product of the two categories you put in. But in order to get the categorical action, you have to throw in some more extensions.
Okay,
and
so
Ruquier kind of
equivalence or something.
Yeah, sorry?
Maybe there is a derived equivalence.
No. It's really kind of like adding in more extra stuff. So there are examples. So if you take a minuscule representation, you'll get a semi-simple category. But when you tensor together two minimals, you don't minuscules. You don't get a semi-simple category. You get a quasi-hereditary category. You get one where there's sort of a series of objects. So somehow the pure tensors become the standard modules of the quasi-hereditary structure, but you have to throw in extra extensions to somehow keep everything running correctly.
Thanks.
Mm-hmm. Alistair, you'd started a question.
Yes, this affine oriented Brouwer category is the central charge 0 Heisenberg category.
I'm aware.
And so if you take out the oriented and you just have the Brouwer category, is there some corresponding non-zero central charge version?
I don't really think so. I mean, it's an interesting question, but it's hard to know what that would mean, right? Because the central charge is about the difference between EF and FE, and now you only have one E.
Exactly.
So I don't think there is, but it is a kind of interesting question.
I also have a basic question. If you think about GLN as GL0N, then in the table you showed us you should get wedge N of the dual. And
no, you get the 0th wedge, which is the trivial module.
Yeah, but so.
You're asking.
If you do GL0N, then you get C tensor wedge N of the dual of the standard for SL infinity. And
yeah, I mean, it's just writing the combinatorics differently.
okay.
I mean, I haven't thought carefully about that particular issue. I mean, I think it's like you have to use the Chevrolet involution. So I think it's you sort of have swapped which one you think of as E and which one you think of as F, and that's enough to take you from the dual back to the original one. But I would need, I think that's exactly the Chevrolet automorphism that you've like negated. So yeah, I mean, there's this, one of them being the standard S infinity and one of them being the dual. I mean, somehow which one is which is kind of arbitrary. Right. So it's, if you do the Chevrolet automorphism, it'll swap the two. I think that kind of answers your question.
Yeah, thank you.
Mm-hmm.
Any other questions? If there are no other questions, then we will go for our break and then in the Gather Town, and then the next talk will be at 11:50. Let's